Hello everyone, I'm Jyoti from BSc Chemistry Honors second year. So this video is for visually impaired students and the chapter name is Ethers and Epoxides from Organic Chemistry. Let's start. Introduction of organic compounds having COC as the functional group are called ethers. Their general formula is ROR dash, where R and R dash may be same or different alkyl groups, or one of them may be an alkyl group and the other aryl group. The divalent oxygen is also called the ethereal oxygen. Um, Ethers in which the group R and R dash are the same are called simple or symmetrical ethers, while those in which the group R and R dash are different are called mixed or unsymmetrical ethers. Classifications: ethers may be broadly classified into following three categories: aliphatic ethers, in which R and R dash may be saturated or unsaturated groups derived from aliphatic hydrocarbons; aromatic ethers, in which either one of the both R and R dash are aryl groups; ethers in which one of the group is aryl while the other is alkyl are called phenolic ethers or alkyl aryl ethers. On the other hand, ethers in which both the groups are aryl and are called diaryl ethers. Cyclic ethers, ethers in which the oxygen is present in the ring are called cyclic ethers. They are further classified in simple cyclic ethers or crown ethers. Simple cyclic ethers. Cyclic ethers containing 1, 2, or 3 oxygen atoms in the ring are called simple cyclic ethers. Cyclic ethers containing at least 4 oxygen atoms are called crown ethers because their three-dimensional shape resembles the shape of a crown. They are usually named as crown ethers, where X is the total number of atoms in ring and Y is the number of oxygen atom. For example, 12 crown 4, 15 crown 5, 18 crown 6. Open chain or acyclic ethers. Common names. The common names of ethers are derived by naming of the two alkyl or allyl groups lying to the oxygen atom in alphabetical order and adding the word ether. In case of symmetrical ether, the prefix D is used before the name of the alkyl or the aryl group. Some aromatic ethers, however, have their special names. For example, methyl phenyl ether is called anisole and ethyl phenyl ether is called phenetol. IUPAC names in the IUPAC system. Ethers are named as alkoxy-alkanes. Their ethereal oxygen is taken with the smaller alkyl group and forms a part of the alkoxy group, while the larger alkyl group is considered to be a part of the alkene. Mm. Acyclic polyethers. Long chain polyethers are named as the oxa derivatives of the alkane corresponding to the total number of carbon and oxygen atoms present in the chain. For example, 2,5-dioxaborane. Cyclic ethers. Common names in the common system. The three-membered cyclic ethers named as oxides of the alkylene from which they are derived. Ethylene oxide or epoxide, in which CS2O CS2 is taken. Propylene oxide and isobutylene oxide structures are also given. The names of some cyclic ethers are based upon the names of their fully hydrogenated products. For example, furan, tetrahydrofuran, 4H furan, etc. The italicized portions of these names are the suffixes used to represent the size of saturated heterocyclic rings other than with enantiomers. In case of substituting cyclic ethers, the substituents are indicated by numerical prefixes with the oxygen atom getting number 1. Oxa names. Cyclic ethers are also named as oxa derivatives of their corresponding cycloalkanes. Methods of formation from alkyl halides. Williamson synthesis. This is one of the best methods of the preparation of ethers. It involves the treatment of an alkyl halide with a suitable sodium alkoxide. The sodium alkoxide needed for the purpose is prepared by the action of sodium on a suitable alcohol. The reaction in fact involves the nucleophilic displacement of the halide ion from the alkyl halide by the alkoxide ion by SN2 mechanism. For example, sodium ethoxide on reaction with ethyl bromide at 330 K give rise to diethyl ether. Similarly, alkyl aryl ethers can be easily prepared by treating sodium phenoxide with alkyl halides. Like halide ions, sulfate ions is a good leaving group. Therefore, in Williamson synthesis, alkyl halides may be replaced by alkyl sulfates. Uh, Sodium phenoxide with diethyl sulfate give rise to phenol with Na2SO4 as a side product. Limitation and proper choice of alkyl halide and sodium alkoxide to be used in Williamson synthesis. Since a halogen attached to a double bond or an aromatic ring cannot be readily displaced by nucleophilic reagent, therefore aryl halides are not generally used in Williamson synthesis. Therefore, for the synthesis of simple alkyl aryl ether, the reaction is carried out between an alkyl halide and the sodium phenoxide and not between aryl halide and sodium alkoxide. Uh, However, if the halogen is activated by the presence of electron withdrawing groups at orthopara, at orthopara positions with respect to the halogen atom, such activated aryl halides can be used in Williamson synthesis. For example, para-nitrobromobenzene with sodium methoxide give rise to para-nitroanisole in the presence of heat. We have stated above the Williamson synthesis involves nucleophilic attack of the alkoxide phenoxide ion on alkyl halide. Now, depending upon the structure, alkyl halide may undergo substitution of elimination reaction. Therefore, for the success of this reaction, it is essential that the alkyl halide used must be such which predominantly undergoes nucleophilic substitution, since primarily alkyl halides are more susceptible to SN2 reaction. Therefore, best yields of unsymmetrical ethers are obtained when the alkyl halides are primary and alkoxides may be primary, secondary, or tertiary. For example, tertiary ether is prepared by treating ethyl bromide with sodium tertiary. The above ether cannot be prepared by treating sodium methoxide with tertiary chloride or bromide, since under these conditions an alkene is that is isobutylene is the main product with secondary alkyl halides. Both substitution and elimination occur together, giving a mixture of esters and alkenes, but with the tertiary alkyl halides, only elimination occurs, giving alkenes. Thus, when a mixture of tertiary bromide is treated with sodium methoxide, tertiary ethyl ether is not formed, but instead 2-methyl propene formed due to elimination reaction. Due to steric hindrance, secondary alkyl halides also prefer to undergo elimination rather than substitution. Reaction of alkyl halides with dry silver oxide. Ethers can also be prepared by heating an alkyl halide with dry silver oxide. Uh, for example, ethyl bromide. 2 moles of ethyl bromide on treating with dry silver oxide give rise to diethyl ether. From alcohols, ethers may be prepared from alcohols as well as ethers may be prepared by the dehydration of alcohol either in the presence of acids or heated alumina. Symmetrical ethers can be prepared by the dehydration of alcohols with concentrated H2SO4 at 413 K. ROH 2 moles of ROH at concentrated H2SO4 at 413 K give rise to ROR plus H2O CS3CS2OH in the presence of concentrated H2SO4 at 413 K gave rise to diethyl ether. Uh, Limitations: this reaction, two molecules of an alcohol lose one molecule of water, therefore it is better called as intermolecular dehydration. Limitations: though this method is useful for the large scale production of ethers, it has two major drawbacks. The preparation of ether is always accompanied by the formation of alkenes due to the intermolecular dehydration of alcohols. However, in case of primary alcohols, the alkenes are formed only to a small extent, which can be further suppressed by using a large excess of the alcohol. In case of secondary alcohols, alkenes are formed in much larger amounts than the ether, but in case of tertiary alcohols, exclusive formation of alkenes occurs. Thus, the order of dehydration of alcohols leading to the formation of ethers follows the sequence primary, secondary, and tertiary. Therefore, dehydration of alcohols is used only for preparing ethers from primary alcohols. The method is not suitable for unsymmetrical ethers because a complex mixture of ether is always obtained. Mechanism is given below. by the action of diazomethane on alcohols or phenols. Methyl ethers can also be prepared in excellent yield by the action of diazomethane on alcohols or phenols in presence of tetrafluoroboric acid. As given, ethyl alcohol, uh, when tetrafluoroboric acid is treated with diazomethane, then on further reaction we will get uh, with when we treat it with phenol, as when we treat the alcohol or phenol in presence of tetrafluoroboric acid with the diazomethane, we will get ethers from alkenes. Ethers can be prepared from relative alkenes by the following two methods: direct addition of alcohols in presence of acids as a catalyst, or the second one is indirect addition of alcohols. Alkenes readily react with mercuric trifluoroacetate in the presence of an alcohol to give alkoxymercurial compounds, which upon reduction with NaBH4 in basic medium give ethers in high yields. Uh, in one group is if one group is methyl and the other is the alkyl group, the reaction occurs by SN1 mechanism and the formation of product is controlled by the stability of the carbocation resulting from the cleavage of CO bond in protonated ether. Since alkyl carbocation is much more stable than methyl carbocation, therefore the alkyl halide is always derived from tertiary alkyl group and the alcohol from the smaller group, that is methyl. For example, butyl ether with the HI concentrated at 373 K, we get butyl iodide with methyl alcohol as a side product. It may be emphasized here that the high polarity of solvent present in concentrated HI has favored a one mechanism. However, if the cleavage of butyl methyl ether is carried out with anhydrous HI in ether, the low polarity of the solvent would favor SN2 mechanism, and hence I negative ion will attack the less hindered methyl group, giving methyl iodide and butyl alcohol. Cleavage of alkyl aryl and diaryl ethers. In case of alkyl aryl ethers, the products are always phenols and the alkyl halide, never an aryl halide and alcohol. The carbon atoms of the phenyl group are sp2 hybridized, while that of alkyl group are sp3 hybridized. A sp2 hybridized carbon, being more electronegative, repels the nucleophile, while the sp2 hybridized carbon, being less electronegative, attracts the nucleophile. In other words, nucleophilic attack by the halide ion occurs more easily on alkyl group, leading to the formation of an alkyl halide and phenol. Secondly, a phenyl group is much bigger in size than an alkyl group. Therefore, because of the steric hindrance of the bigger phenyl group, the halide ion attacks the alkyl group, leading to the formation of an alkyl halide and phenol. It may be, however, be noted that phenol is not converted to iodobenzene even with the excess of HA. Diaryl ethers are not cleaved by HI because both the carbon atoms to which oxygen is attached are sp2 hybridized and hence repel the nucleophilic halide ions. Chisel method: cleavage of alkyl aryl ethers by hydroiodic acid forms the basis of Chisel method for the estimation of alkoxy groups such as methoxy and ethoxy group. In such ethers, a known weight of the phenolic ether is treated with an excess of concentrated hydroiodic acid. Uh, the alkyl iodide produced as a result of cleavage of ethers by HA is treated with an phenolic solution of silver nitrate. The precipitate of silver iodide thus formed is filtered, washed, dried, and weighed. From the amount of AgI formed, the percentage of alkoxy groups can be estimated. With sulfuric acid, on heating with dilute H2SO4 under pressure, ethers are hydrolyzed to alcohols. When heated with concentrated H2SO4, ethers react in the same manner as the halogen acid is to form an alcohol and an uh, alkyl hydrogen sulfate. Secondary and tertiary ethers, however, form alkenes. Reactions involving the alkyl group, action of air and light, autooxidation, formation of peroxides when exposed to air and light, For a long time, ethers are oxidized to form hyperperoxides or simply peroxides. It is a free radical reaction, and oxidation occurs at the carbon atom next to the ethereal oxygen to form hydroperoxides. The peroxides are very dangerous compounds since they decompose violently at high temperatures. Therefore, serious explosions may occur during distillation of hot samples of ethers. If peroxides are not removed, presence of peroxides in old samples of ethers may be detected by shaking them with a freshly prepared solution of FeSO4 followed by addition of KCNS. Appearance of a red color indicates that the presence of peroxide. Simple method to remove peroxide is to shake an old sample of ether with either an aqueous solution or Ki or a ferrous salt. When ether peroxides are reduced to either an ion negative, ion is oxidized to I2, or Fe3 positive salts are oxidized to Fe3 positive salts. Halogenation. Ethers react with Cl2 or Br2 to give substitution products. The extent of halogenation, however, depends upon the reaction conditions. For example, diethyl ether reacts with the chlorine in dark to give alpha dichlorodiethyl ether. However, in the presence of light and excess of chlorine, all the hydrogen atoms are substituted to give perchlorodiethyl ether. Epoxides, the three membered cyclic ethers are called epoxides. In the common system, they are called alkyline oxides, but in the apex system, they are called either alkane oxide, epoxy alkanes, or oxiranes. For example, the examples are given below. Synthesis of epoxides. There are two main laboratory methods for the synthesis of epoxides. These are epoxides of alkenes, alkenes on treatment with peroxy acids, also called peracids, such as benzoic acid, chlorobenzoic acid, peroxy trifluoroacetic acid, etc. In an inert solvent such as CS2, Cl2, ClCl3, or CCl4 give epoxides. Due to the formation of epoxides, the oxidation of alkenes with peracids is commonly known as epoxidation. For example, as the alkene, for example, ethylene peroxybenzoic acid in the presence of CCl4 will give rise to ethylene epoxide with benzoic acid. From halohydrines. When halohydrines prepared by addition of hypohalous acids to alkenes are treated with a base, X is eliminated and an epoxide is formed. For example, cyclohexene with on treated with Br2 in the presence of H2, transaddition of OHBr or trans 2 bromocyclohexanol, then or treating it with dilute NaOH, we will get 1 epoxy cyclohexane. And in the case of ethylene with Cl2H2, we will get ethylene chlorohydrin. On further treatment with KOH, we will get ethylene epoxide or potassium chloride as a side product with the water. Manufacture of ethylene oxide. It is manufactured by passing a mixture of ethylene and air under pressure over silver catalyst at 573 K. Chemical reactions of epoxides. Cyclic ethers are cyclic ethers containing 5 and 6 membered rings, such as tetrahydrofuran and 1,4-dioxane, and quit inert are often used as solvents. Three-membered cycloethers, that is epoxides, on the other hand, are highly reactive. This is due to the reason that the three-membered rings are highly strained, that is, they have considerable angle strain. Because of their highly strained nature, epoxide ring can be opened by a variety of nucleophilic reagents under the much milder conditions. Consequently, most of the reactions of epoxides are the ring opening reactions. These can be catalyzed both by acids and bases. Acid catalyzed ring cleavage of epoxides due to the large angle strain. Epoxides are readily electrolyzed by dilute mineral acids at room temperature to form corresponding 1,2 diols. For example, ethylene epoxide with water in presence of mineral acid give rise to ethylene glycol. Similarly, halogen acids and alcohols in presence of acids can bring about the cleavage of epoxides. Base catalyst ring cleavage of epoxides. Unlike ordinary ethers, epoxides can also be cleaved under basic conditions. Ethylene oxide with water in the presence of OH negative give rise to ethylene glycol. Similarly, sodium oxide and ammonia amines can also bring out cleavage of the epoxide ring. Um, reduce selectivity orientation of a cleavage of epoxide. Unsymmetrical epoxides can undergo ring opening in two different directions and hence can give different products under acidic and basic conditions. In acidic medium, the nucleophile generally takes the more substituted carbon, while in basic medium, the nucleophile takes the less substituted carbon. Although both the reactions occur by the acid mechanism, the difference difference lies in the stability of their transition states. In the acid catalyst cleavage of epoxide due to protonation, each epoxide atom carries a small positive charge, the magnitude of which depends upon the substitution. Since atoms highly substituted carbon can accommodate positive charge better, therefore more highly substituted has a fair amount of carbocation character and hence gets attacked by the nucleophile. Thus, in contrast, a base catalyzed reaction there is no protonation and hence none of the epoxide carbon has a fair amount of carbocation character. Therefore, like SN2 reactions, the attack of nucleophile is controlled by the steric factors. Evidently, the nucleophilic attack will occur preferentially at the less hindered carbon atom. Thus, stereochemistry of ring cleavage of epoxides, both acid and base catalyzed ring opening reactions of epoxide occur by SN2 mechanism. Therefore, attack of the nucleophile always occurs from the backside, leading to the formation of trans 1,2 diol. Reaction with Grignard reagents and organolithium reagents. Epoxides also undergo ring opening reactions with Grignard reagents and organolithium compounds. The addition products initially formed upon hydrolysis give primary alcohols containing two carbon atoms more than the Grignard or the organolithium compounds. The epoxide generally used in these reactions is ethylene oxide. Uh, Thanks for watching.